Hello, and welcome to Today for College Algebra, Section 5, Rational Expressions. Rational expressions simply means fractions. So today we're going to work with fractions, whether we're going to work with domain restrictions in general, add, subtract, multiply, and divide fractions, and simplify as best as we can. So, first, domain restrictions. There are three main things that come up. You can never ever divide by zero, so something like 3 over x could not equal zero right there because it's in the denominator. Can't have negatives in an even radical, which should make sense. Square root of x would have to be greater than or equal to zero. Otherwise, it would create an imaginary number. And one you're probably not familiar with as much, but we have talked about it. No zeros or negative in a logarithm. So if I have log of x would have to be greater than 0. X cannot even equal 0, so that's a little bit different there. So if we use interval notation for all of these, this top one, we would get, negative infinity to 0, union 0 to infinity, because x can be anything other than 0. Here, we would get bracket 0 to infinity, because x could be 0. And here we would use it as, a parenthesis, because the equal to wouldn't work. So find the domain interval notation. We see that we have a fraction. So I know that x plus 5, because that's the entire denominator, cannot equal 0. Well, if we get x by itself by minus 5 minus 5, I know that x cannot equal negative 5. But it can equal everything else. So everything else would be negative infinity to negative 5 union negative 5 to infinity. The important thing is, again, I have these parentheses, so I get every value below up to negative 5, but negative 5 is not included, and every number after negative 5 that's not included negative 5, which is nice. Here, same idea. I have an even radical. So I have x minus 3. So x minus 3 has to be greater than or equal to 0. So we can just add 3, add 3. So x has to be greater than or equal to 3, which would mean x is from 3 with a bracket, because it can be equal to, all the way up to infinity. Now, we have talked about that being an even radical, so this would be the same thing for like fourth root, etc. The reason we stress that idea of it being an even radical is if it was an odd radical, such as cube root of 3, and let's say we did negative 27. Well, that actually works, because that could be negative 3 times negative 3 times negative 3. Recall that an odd radical just means that's how many numbers it takes to equal this inside value. Well, negative times a negative times a negative would still be a negative value. There's no possible way for us to multiply 4 or 6 or any increment of an even number of negatives to get a negative value. That's why there's that restriction there. Here we have the polynomial x squared minus 4x plus 11. There's no fractions. There's no radicals that are even, and there's no logarithm. So there's actually no restrictions here. So this would be all real numbers, or from negative infinity to positive infinity. There's no reasons that this would cause issue. Shoot. Here we have log of x plus 2. Well, again, underneath a logarithm has to be greater than 0. So minus 2, we get that x has to be greater than 2. I'm sorry, negative 2. So we would get from negative 2 to infinity with a parenthesis because it can't be negative 2. Next, rational expressions. A fraction has a polynomial and a numerator and the denominator. And we want to simplify. The first thing I would do is factor everywhere you can. So in this first one, in my numerator, I have x squared minus 4. Well, that simply turns into difference of squares. So my numerator would be x minus 2 and x plus 2. And my denominator is still x minus 2. Now, conceptually, in order for you to quote-unquote cross things out, they have to be factors, aka multiplicative powers. So the x minus 2 and x minus 2 here can be crossed out. Now, if I go to this next one, I can't actually factor anything out of my numerator, so I'm left with 5x minus 4. But in my denominator, I can take an x out of both of those things, so I get x and x squared minus 2. Here, you might think difference of squares for a second because there's a minus. They were different. This is squared. Unfortunately, 2 does not have a does not have a square root or perfect square root, so I wouldn't do difference of squares here. I guess you could write x minus square root of 2, x plus square root of 2. Doesn't actually help us and makes my denominator a little more murky. And then again, nothing to cross off, so I'd be left with this. And then in my last fraction, there's nothing actually for me to actually factor out. You might look at the denominator and think it's factorable, but it unfortunately isn't. So what does this mean in terms of our restrictions? Well, one thing that you might notice is in here, on this left fraction with the red, I crossed out my denominator, so I don't have a denominator anymore. Unfortunately, this is still technically a restriction. X can still not equal 2. Whereas the other ones, I'm going to flip back for a slide for a second, x couldn't equal 5. You would get a graph that would have some sort of weird pattern. In fact, let's take a look at it. We might as well. Alpha y equals, it was 4x over x plus 5. Let's go zoom standard. We get this vertical asymptote at negative 5. So the graph looks like where we get this vertical asymptote at x equals negative 5. Sorry for my poor penmanship. Charging my pen, it's all messy. It's not really reading sometimes. So x can never equal negative 5 there. That's a vertical asymptote because this stayed. However, if I were to graph this one right here, which we can look at, it breaks down linearly, which makes sense because when we broke it down, it turned into just this x plus 2. That's all it was at the end, which would be a line. However, when I go to look at my graph, it doesn't really show up well on here, but if I go to my table, you'll see at x equals 2, we get an error. That's because of this right here. The graph should actually look like this. It creates that line where we get this x plus 2 pattern, except what happens is there's actually what's called a hole in the graph right here because x cannot equal 2. So we get this hole in the graph right there, which is kind of interesting. So we actually still get a restriction even though it's no longer being divided. One thing with division is please, please, please do not do this. Not allowed. Not allowed. You can only cross out factors. Factors being the product of multiplication. This is a section of different terms between addition and subtraction. You cannot do that. Here, if I factor everything out though, now these are being multiplied. Now I can do that. And as you can see, I was a little annoyed when I wrote this slide. Okay, so simplify the following expressions. Let's factor everything. First, let's factor the numerator. What multiplies to negative 12 that adds to positive 4? That sounds like x plus 6 and x minus 2. And then let's factor my denominator. Looks like I have a two terms. I have binomial, so I can factor out a monomial term. I'm just going to divide them both by 3. So I would get x minus 2 as well. And the x minus 2's cancel, so we would get x plus 6 over 3 would be the simplification thereof. Again, please do not cross these out and write x plus 3. That's no good. Over here, I can factor out a 2x of my numerator. So 2x gives me x squared plus 2x minus 3. And then I can factor out a 2x of my denominator as well. 2x, x plus 3. But then I look at this trinomial right here, and I can factor that out even further. What multiplies to negative 3 that adds to positive 2? That would be x plus 3 and x minus 1. I still have the 2x up top, all over 2x, x plus 3. And here we get a double cross off, so all I'm left with is x minus 1 for that simplification. Here, let's see, here I get addition of squares, so I actually can't break down my numerator. And then in the denominator, what multiplies to 4 adds to negative 9? Nothing. So this actually is as simplified as it can be. When you're multiplying, I recommend factoring things first, because instead of foiling this whole thing out, not foiling the distribution property, this whole thing out, and then simplifying, I might get things that I can cross off right away. So for example, as I've already broken down, the red factors into 2x minus 3, x plus 2. The blue factors into x, x minus 2, x minus 1. The green, x plus 5, x minus 1. And then the orange, 2x, 2x minus 3. I can treat them as in similar situations. So the red in the orange there, I have one on top and one on bottom for that 2x minus 3, so I can cross that off. Same idea here, x minus 1, x minus 1. And it looks like, oh, and then of course the x and the x right there. And looks like that is as simplified as it can get, so I end up with x plus 2, x minus 2 over x plus 5 and 2 out front. So factor first. You might just cross some things off and save yourself some time. So dividing, very similar. You just keep the first fraction the same, change this into a multiplication sign, and flip the second fraction. So I'm going to get x squared minus 16 over x plus 3 times 2x squared minus 18 over x minus 4. Now again, I could multiply all this, or I can factor right away. Well, x squared minus 16 turns into difference of squares. So that's going to give me x minus 4, x plus 4. X plus 3 is not going to simplify out. There's nothing I can factor out of that. 2x squared minus 18, I can take out a 2 of both of those, so I get 2x squared minus 9, and then the x minus 4, nothing I can do there. But here in blue, I have x squared minus 9, so instead of that, I'm going to write x plus 3, x minus 3 for difference of squares. Now looking around, what can I cross off? Well, I have x minus 4, x minus 4. I have x plus 3, x plus 3, and nothing else. So I would get 2, x plus 4, x minus 3 up top. And in the denominator, I just get 1. So this is all over 1, or just simply that. Adding and subtracting, recall we need a common denominator, same denominator here. So I just add and subtract the top ones, 5 plus 2 giving me 7. My denominator stays the same. Here I have 5 over 2x, and I have 2 over x. So I like to break it up into factors. So this is 2 times x, where this one just has a factor of x. So this second fraction is missing a 2. So I'm going to multiply by 2 over 2 for the second one. So I get 5 over 2x plus 4 over 2x, and then I can add them to get 9 over 2x. This idea here is pretty self-explanatory, but works because what is 2 divided by 2? That'd be, of course, 1. So multiplying by a value of 1 does not change the value of that second fraction. Over here, we have 2. That's the only factor on this side. And then remember, x minus 3 is a whole factor. X minus 3 is all one thing for a factor. So I'd multiply the first fraction by x minus 3 over x minus 3, and I'm going to multiply the second fraction by 2 over 2. Well, this 5 gets distributed to both terms, so 5x minus 15 over the over the denominator of 2 times the quantity of x minus 3, plus 2 times 2 is going to give me 4 over the factor of 2 times the quantity x minus 3. You can distribute the denominator. You don't have to. I keep it in factored form. Then from there, we're just combining like terms. Negative 15 plus 4 gives me 5x minus 11 over 2x minus 3. Here, I have x minus 3 as one thing, and I have x plus 4 as a different thing. So I'm going to multiply the second fraction by x minus 3 over x minus 3. It's missing that factored term. And this one I'm going to multiply by x plus 4 over x plus 4. Distributing the x, we're going to get x squared plus 4x over x plus 4, x minus 3, minus 2 times x, 2x, 2 times negative 3, negative 6, x plus 4, x minus 3. I'm subtracting this fraction, so I'm going to treat that as a keep, change, flip, where I'm distributing the negative, and then from there I can combine like terms. So we would get x squared plus 2x plus 6 all over x plus 4, x minus 3. The last step I would do is check to see if I can factor my numerator, because I might be able to cancel some things out. Well, what can I multiply to give me 6 that adds to give me 2? I can't think of any. So I would say this can't be reduced, and I would leave it as is. If this was like negative 5x, for example, you could see how if you ended up with x squared minus 5x plus 6 over x plus 4, x minus 3, my numerator could have turned into a factor of x minus 3, x minus 2, and therefore I would not be done simplifying, because then I could cross out my x minus 3's. So that's something you should be on the lookout for. It just didn't happen in this example. Last but not least, complex fractions. It's just a fraction within a fraction. There's a couple ways to go about handling this. One is turn everything into a fraction with the exact same denominator. So for example, any common of these numbers is over 1, of course. This is over 1. And if I break apart, I notice this is a fraction of a denominator of x. This says 2. So I'm going to multiply this by x over x, and this by x over x. So up top, I get 1 minus x over x, just subtracting the 1x term, turning into one fraction. And over here, I get 2x plus 1 over x. The advantage to this is now I can multiply by x over x to the entire big fraction. Well, if I do that, if you look in green, I'm dividing by x, but now I'm multiplying by x. So these x's cancel out. And down here in red, I'm dividing by x, but I'm also multiplying by x, so these cancel out. You can also think about it like this. This blue x up top is the same thing as x over 1. So if I'm just looking at the top part, that would be 1 minus x over x times x over 1. Again, this is parentheticalized, which get the same result of I have an x in the top and in the bottom. The same logic applies to the denominator fractions. So I'm left with 1 minus x up top over 2x plus 1. Sometimes that's the quickest way to go about doing things. Otherwise, you could just do one at a time, which I'm going to do over here. So, same idea logically. Let's start with the top. I have 3 over 1, and the bottom I have 1 over 1. Well, my top 3 needs an x in its denominator. So I'm going to multiply that by x over x. The bottom one, I have 1 over 1. It needs this x minus 1. So I'm going to multiply that one by x minus 1 over x minus 1. So let's just rewrite our new top and bottom. I didn't do anything to the first fraction, so I have 2 over x minus 3 times x, so 3x, over 1 times x, so x. And in the denominator, I would distribute the 1 to both of those terms, so I would get x minus 1 over x minus 1 minus 1 over x minus 1. And I can resolve them both separately. So 2 minus 3x, that's just going to give me 2 minus 3x over x. And in the bottom, we have x minus 1 minus 1. Well, negative 1 minus 1 is negative 2, so x minus 2 for x minus 1. Here, I just have to recall, conceptually speaking, that this entire fraction bar just means fraction or division process. So this whole thing can be rewritten as 2 minus 3x over x divided by x minus 2 over x minus 1. And again, remember that I can divide fractions by keeping the first one the same. So 2 minus 3x over x, flipping the division sign into a multiplication sign, and then flipping my fraction, aka just multiplying by its reciprocal. So I would get x minus 1 over x minus 2. And here I would try to factor and cross things out. Things don't factor or simplify out very nicely. So I end up with just 2 minus 3x times x minus 1 over x times x minus 2. And that would be my answer there. Thank you for listening, and I hope you have a wonderful day.